Guys, welcome to Unit 11. Today we're going to start off Unit 11 by introducing to you some terminology around polynomials. So pause the video now and complete the definitions at the top part of your notes on polynomials. All right, now that we've completed those definitions, let's take a look at a few more terms that we are going to get familiar with. There are different classifications of polynomials based off of their degree. A linear polynomial's parent function is y equals x. The degree of that polynomial is 1, and we've looked at plenty of examples throughout the year. So, for example, 3x, or you could say 4x minus 2, so on and so forth. Lots of different examples of linear polynomials. A quadratic, the parent function of the quadratic is y equals x squared. The degree on that is 2. And there's examples all over the place, such as negative 2x squared, or you could say x squared minus 25. These are all examples of quadratic polynomials. The next one is a cubic. The parent function there is y equals x cubed. The degree on that polynomial is 3. And again, lots of different examples. So you could have something like 3x cubed minus 4x squared plus x plus 7. So there's an example of a cubic polynomial. Next one is quartic. As you may have guessed, that's x to the 4th. The degree on that is the 4th degree. And again, plenty of examples. You could have something like 2x to the 4th minus 4x squared plus 7, and so on and so forth. Lots of different examples. Finally, the quintic is x to the 5th. The degree on that is 5. And you go ahead and come up with your own example for a quintic polynomial. All right, let's move into our examples now. So for today, we have this example here. It says list all of our coefficients of this polynomial defined by 3x squared plus 6x to the 5th minus 47 minus 8x squared. So our coefficients, remember, are the numbers in front of those variables with the powers. So our coefficients are 3, positive 6, negative 47, and negative 8. Next, it says to rewrite in standard form. So as you learned by copying down the definition, standard form means in decreasing order. So as I scan my polynomial, I'm going to start by combining my like terms and then rewrite that in standard form, and therefore that's decreasing order. So my largest term here is positive 6x to the 5th. My next term is the squares, and I'm going to combine those to give me negative 5x squared minus 47. Next, it says what are the degree and the leading coefficients of this polynomial. So notice this is the same polynomial as the one up above it. And so we're going to just take the leading coefficient. That's the coefficient on the term with the highest exponent. So our leading coefficient we'll abbreviate as LC. That is equal to 6. And the degree of this polynomial is a 5th degree. So that is the largest exponent in the terms of that polynomial. So it's degree 5, so that's an example of a quintic polynomial. All right, example 2 says to consider this polynomial now, 6x to the 5th minus 3x to the 4th minus 2x minus 70. Find p of 2. So remember, whenever we see the 2 in the parentheses there, that means we are going to substitute that 2 in for x into our polynomial. So that will read 6 times 2 to the 5th minus 3 times 2 to the 4th minus 2 times 2 minus 70. So now we're going to evaluate this by using our order of operations, PEMDAS. So we'll do 2 to the 5th first. So that becomes 6 times 32 minus 3 times 16 minus 4 minus 70. Now, once we do all that, or we let our calculator do all that, we should come up with the answer of 70. So P of 2 is equal to 70. All right, next it says to sketch the graph of the function on this window from negative 3 to 3 on the x-axis and negative 120 to 10 on the y-axis. So we're just going to make our nice little graph here. This is negative 3. Here is positive 3 on our x-axis, and we're going to go all the way down to negative 120 on our y, and then positive 10 would be somewhere right around here on our y-axis. So I actually have already done this in Desmos. Desmos allows us to do a really nice job of graphing this and getting a visualization of what that looks like. So you can see here that we have this guy graphed. Our polynomial is 6x to the 5th power minus 3x to the 4th minus 2x minus 70, and then we graph that in the range from x is between negative 3 and 3. So you can see here, whoops, hopefully that will stop moving around on us. Doesn't look like it will stop moving around on us. There we go. Well, that thing's really freaking out. It's doing the dance here. Woo, in, out, in, out, in, out. All right, well, you get the idea of what that looks like. Hopefully your Desmos isn't freaking out like mine, doing the Desmos boogie. We'll go back and go ahead and sketch that graph as best you possibly can. So it looks like it's going to come up. It's going to cross our y-axis right around -70 and then continue on up. And our y-axis was here at 0 over and -70 down. All right, let's move into our next example here. It says let f of x equal 5x to the third, and I left a little blue poop trail there on the paper for some reason. All right, let f of x equal 5x to the third minus 3x squared plus 4. G of x is 2x plus 6. Now it says predict what's going to happen when we do the following. So this says that we're going to try to predict the degree of f of x times g of x. In other words, if I were to take 5x cubed minus 3x squared plus 4 and then multiply that to the function 2x plus 6. Now, what we're going to have to do in this case is do this distribution property. That I'm going to have to multiply each term in my first polynomial by each term in my second polynomial. And if we wanted to predict the degree, remember the degree will be the highest exponent. Well, that's going to occur when I multiply the highest power in one polynomial to the highest power in the other polynomial. So I can obtain the degree of my product of these two polynomials by simply multiplying my 5x cubed and my 2x. When I multiply those, I'm going to get 10x to the fourth. So I'm going to say that the degree of this product will be 4. It will be a quartic polynomial. All right, now it says to predict the leading coefficient of this product. Well, again, we have this product set up. The leading coefficient will always be the coefficient on the term with the highest power, and as we just found out, that's going to be 10. All right, next it says to predict the degree of the composite function f of g of x. So now if you remember back a few units ago, we studied these composite functions. We can obtain the composite by taking the function g of x, that's 2x plus 6, and substituting it into our other equation every time we see an x. So that will look like this: 5 times 2x plus 6 to the third power minus 3 times 2x plus 6 squared plus 4. Now, if we want to predict the degree here, we have to expand this polynomial out. And what that means is we're actually going to have to cube this 2x plus 6. So when I cube 2x plus 6, that will be like multiplying it by itself 3 times. So I'm going to say 2x plus 6 times 2x plus 6 times 2x plus 6. And then in front of that would be a 5. So if I were to actually evaluate this first term here, it would be 5 times the product of 2x plus 6 times 2x plus 6 times 2x plus 6. Now the degree of that would be obtained by multiplying the 2x times the 2x times the 2x. And that would give me 8x cubed. And this would actually be the highest power in this composite function. So the degree here is going to be at most 3. Now it also says to predict the leading coefficient of this composite function f of g of x. So again, going back here, I have 2x times 2x times 2x, which gave me 8x cubed. However, I'm also going to multiply that 5 into that product, and that will give me 5 times 8x cubed. And my leading coefficient then would be 40, because that would be the coefficient on 40x cubed. So my leading coefficient of this composite function would be 40. All right, let's take a look at a story problem here. Here is Sally and her family. They start saving for college, never a bad idea, when she graduates from 8th grade. And at the end of each grade, they deposit the amount below into a fund with a 4.2% interest. So this is growing constantly. How much will she have by the time she graduates high school? So this is similar yet different to the problems that we've studied in previous chapters. After the summer of her 8th grade, she has $2,000. And that $2,000 is going to earn interest of 4.2%, which is 1.042, and it's going to earn interest for the next 1, 2, 3, 4 years. So that interest needs to be compounded 4 times annually. And then, in addition to that, she's also made the next summer $2,500, and that's also going to be deposited and earn the same interest. So we're going to multiply it by the same growth factor. However, now it's only going to earn interest for 1, 2, 3 more years. All right, well, she does the same thing. The next summer, she earns $2,200, and that's going to be deposited in the bank, earning that same 4.2% interest. However, now it's only going to sit in the bank for 2 years. The next summer, she's going to earn $2,050, and that's going to earn interest for 1 year. And then finally, her 12th grade year, she makes $2,100. So this is a polynomial function that represents the total amount of money that she's going to have in her bank account when she graduates from high school and going into college.